Here are two attention patterns from the same sentence. One is shifted by 50 tokens. Watch what happens when we apply RoPE. They overlap perfectly. This tiny rotation makes attention care about relative position, not absolute. That's the shift invariant property we'll build from scratch today. Quick roadmap. We'll start with intuition, then the one-line math property, then minimal code, then how to scale context safely, and finally, common pitfalls. By the end, you'll understand why models like Llama use RoPE and how to extend context beyond training length. Transformers are permutation invariant. Shuffle the tokens, and the self-attention mechanism doesn't care. That's a problem because word order matters. We need to inject positional information somehow. The classic approach is absolute positional encoding. Add sinusoids to token embeddings. Simple, but not relative. An alternative is relative positional bias, added directly to attention logits. That's distance-aware, but adds compute. RoPE finds a middle ground. Here's the core idea. Take each pair of dimensions in your query and key vectors and treat them as a 2D point. Now rotate that point by an angle that depends on the token's position. Higher positions rotate further. When you compute the dot product between a rotated query and a rotated key, the result depends only on the difference between their positions, not the positions themselves. The key property is this identity. The inner product of two rotated vectors equals the inner product of the original query with the key rotated by the relative distance. This follows from the cosine angle difference formula. The rotation matrices cancel out the absolute positions, leaving only n minus m. That's why RoPE is shift invariant. We don't use a single frequency. Instead, theta I decreases geometrically across dimensions, controlled by a base parameter, typically 10,000. Low-frequency bands capture long-range patterns. High-frequency bands capture local structure. This multi-scale schedule is what makes RoPE effective across different context lengths. Let's see it in action. Here's a query at position 5 and a key at position 8. We apply the rotation using the rotate half trick. Swap even and odd indices, negate, and combine with cosine and sine. Now shift both positions by 10. The dot product stays almost identical. That's the invariance guarantee in practice. Here's the minimal PyTorch implementation. Compute inverse frequencies, then use einsum to broadcast across positions. Concatenate to match the head dimension, take cosine and sine. The rotate half function swaps and negates pairs. Multiply the original vectors by cosine, add the rotated halves times sine. That's it, RoPE in 15 lines. Where does this sit in the attention stack? After projecting Q, K, and V, you apply RoPE only to Q and K, not V. Then you compute attention as usual, Q times K transpose softmax times V. RoPE happens per head before the attention scores. What about long context? If you push beyond the training window, the model sees out-of-distribution rotation angles. Oscillations and aliasing can hurt performance. The curve drops off a cliff. Naive extrapolation doesn't work. You need principled scaling. Two foundational techniques are position interpolation and NTK-aware scaling. PI compresses positions back into the trained range by scaling them down. NTK adjusts the base frequency so the rotation angles stay smooth. Both help, but they trade off short-range fidelity for long-range stability. Yarn and LongRoPE go further. Instead of scaling all frequencies uniformly, they blend ranges. Low-frequency dimensions, which handle long distances, get scaled more aggressively. High-frequency dimensions, which preserve local structure, are left closer to the original. This preserves short-range quality while enabling much longer context. In practice, you have several knobs. Base controls the frequency grid. Smaller base means faster oscillation. Partial rotary factor lets you rotate only a fraction of the head dimensions for stability. And when using KV cache, you just continue the position IDs from where the cache left off. RoPE composes cleanly with caching. For multimodal models, you can extend RoPE to 2 dimensions. Split the head dimensions in half. One half rotates by height position, the other by width. This gives you spatial awareness for images or video, using the same rotation principle. A few things to avoid. Don't rotate V, only Q and K. Aggressive scaling can degrade short-range attention, so validate on your actual use case. And remember, aliasing still happens if you go too far out of distribution. Scaling helps, but it's not magic. 3 things to remember. 1. Transformers need order, and RoPE provides it by rotating Q and K. 2. The dot product depends on n minus m thanks to the rotation property. 3. The code is simple. Rotate half trick, cosine, sine. You now understand why Llama and modern long context models use RoPE. If this clarified RoPE for you, please consider subscribing. See you in the next one.